This is Unit 4, Lesson 4, Part 2, Related Rates. And we're going to start with an example. The top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what is the rate of change of the distance between the bottom of the ladder and the wall? Now, this is a problem where a drawing definitely helps because it's not extremely obvious what the equation that we're going to use is. So what does it look like? We're going to start by drawing a wall. So there's my wall, and here's the floor. And we're going to put a ladder along this wall. Okay, so there's our wall, there's our floor, and we have a ladder that is 25 feet long, that's leaning against a wall, and it's traveling downward that way. Okay, and as it moves down the wall in the horizontal direction, it's going to move to the right. It's going to slide down the wall. So if we give some variables to our drawing here, we can have that x is here. X is the horizontal and y is the vertical. So what kind of shape do we have? We have a right triangle, and we're looking at the side lengths. Now we want to do this when y is 7 feet. What is going to be our rate of change of the ladder? So we're going to know, we need to know what value x is. So we have a lot of information now to get started. So the equation we're going to use is the Pythagorean theorem. So we're going to use c squared equals x squared plus y squared. We are given c is 25 feet. We are given a specific y is 7 feet. And we're given the rate of change of y. It's sliding down the wall at a rate of -3 feet per minute. Okay? So we need to find how fast it's moving along the ground. So that is our dx dt. All right, so the first thing we want to do in this problem is, I like to do this. A lot of people will do the rate of change first and then go back, but I'm missing one thing. I need to know that x. So I want to find that x. So I'm going to substitute in the values I have for that specific instance, which is 25-foot ladder does not change, but we have a specific y, which is 7 feet. And so I'm going to solve the Pythagorean theorem for x for this case. And I get x squared is 576. So x is 24. That's one of our Pythagorean triples. If you knew that, you didn't have to do this step. You could have just written down that x was 24. Now what I'm going to do, my step 2, is going to differentiate my Pythagorean theorem. And I can put in the 625 because that's a constant. The length of the ladder is not changing. It's not a folding ladder or anything. And now I can differentiate this with respect to time. So I have 2x dx dt plus 2y dy dt is going to equal 0. Solving this for dx dt, I can get rid of those 2's. So I have y dy dt. Actually, let me do it the other way because I'm solving for dx dt. So I'm going to have x dx dt is going to equal -y dy dt. And so then dividing both sides by x, so I have dx dt is going to equal -y over x dy dt. So now what I can do is I can substitute in my values and find my change in x. So dx dt when y equals 7 is going to equal -7 over our 24 times our rate of change of the y. So remember, put feet, and this is going to be feet per minute. Okay? And of course, these feet will cancel and I'll be left with feet per minute, which is what I want. So dx dt is going to equal 7/8 is what this comes out to be, feet per minute, and you can leave it that way, at y equals 7 feet, and that's going to be our answer. Okay, so that comes up a lot where you're using the Pythagorean theorem. Another one that comes up, they ask, and we'll do some of these too later, is how is the angle changing? So then we're going to involve trig relationships like cosine, sine, and tangent. But we're going to start with the basics right now. Next example. At noon, a ship, A, we're going to call it, is 150 kilometers east of ship B. Ship A is sailing west at 35 kilometers per hour, and ship B is sailing north at 25 kilometers an hour. How fast is the distance between the ships changing at 4 p.m.? So, a couple things to note here is that you have a time change of 4 hours. So that 4 p.m. gives us a T of 4. Okay, so we need a picture. So what we have here is we have ship A is right here in the water, and it is traveling east. And at the same time it travels east, ship B is moving north this way. Oops, didn't mean to do that. Because ship A is traveling this way and ship B is going this way. So what we want to find is how is this distance between them changing? Okay, that is our rate of change. So we originally know that this distance here was 150 kilometers. So I am going to label this side as 150 minus x, how far away it is. So if I have its x coordinate and I subtract it from 150, I'll always know how far away it is from where B is traveling north. And the other side I am going to call y, because that's the vertical direction. And really what I'm looking for is this slanted side between A and B, which I'm just going to use z. Let me use a different color. Let me use red. Call this side z. Okay? So this is again a Pythagorean theorem problem. So what do we know? We know that x squared plus y squared equals z squared. So now z is not a constant like in the ladder. So what we really have here is 150 minus x squared plus y squared is going to equal z squared. All right, so what are we given? We are given the rate of change of our x and our y. We know dx dt, that's how fast ship A is moving. It's moving at 35 kilometers per hour. And we know the change in ship B, that's its speed, is 25 kilometers per hour. I'm sorry, yeah, per hour. And then we also know that T is 4. We're going to need that as well after 4 hours. Okay, the reason why we need that is in order to find dz dt, we're going to have to find the position of those ships because we're going to need what their x position and their y position is. So the first thing I want to do is, move this up just a little, is I want to find out at 4 p.m. So that means T equals 4. I want to find ship A and ship B's position. Okay, and then I can find the Z at that specific position too. So ship A is going to be, it's traveling for 35 kilometers. Sorry, that was my watch. 35 kilometers per hour. Times 4 hours. So its position is going to be 140 kilometers. And then ship B, traveling north at 25 kilometers per hour for 4 hours is going to be 100 kilometers away from where it started at noon. And then the other thing I need is I need to find z, so at that specific point. So now I have my x and y, and now I can find my z. So using my equation above, so I have 150 minus the 140 plus 100 squared is going to be z squared. So so I have 10 squared plus 100 squared equals z squared. Simplifying this, z is going to be the square root of 10,100. So z becomes 10 times the square root of 101. All right, so I have all the information I need to get started on this. Okay, so now I can take my original Pythagorean relationship, which was 150 minus x squared plus y squared equals z squared. And I can differentiate with respect to t. So I'm going to bring the power down, lower the power by 1, and then multiply by the derivative of the inside function, which is -1. So I'm just going to make that negative. And then I have my dx dt, because I'll have -1 dx dt. And then next I'm going to have 2y dy dt. And that's going to equal 2z dz, dz dt. Okay, so remember what you're trying to solve for. You're trying to solve for dz dt. So now what I can do is I just got rid of all the 2's because I have a 2 in this term, a 2 in that term, and a 2 in that term. Okay, so now I can just substitute and simplify. So I'm going to have -150 minus 140. And dx dt is 35 kilometers per hour. Plus my y is 100. It was 100 kilometers times 25 kilometers per hour. And I'm going to put that right here. That equals my 10 times the square root of 101. I'm sorry. I moved that over a little more so it's on the screen. That's going to equal my 10 times the square root of 101. And that's going to be times dz dt. So now it's just a lot of algebra to clean up here. So simplifying that previous line, this part becomes -350 because I'm going to have 10 from the 150 minus 140 and then the negative sign, and then I have times 35. So I get -350, and right now I have kilometers squared per hour. And then plus the other term comes out to be a nice simple 2,500 kilometers squared per hour. And that's going to equal my 10 times the square root of 101 dz dt. And then simplifying, putting the left side together, I get 2150, and I'm going to divide that by the 10 times the square root of 101. Because these two will get added together, then I'll have to divide by the 10 times the square root of 1, and that'll give me dz dt. And simplifying that, I'm going to assume I don't have a calculator, so my final answer is going to be the 10s will cancel here. 215 over, you could leave it like that actually as long as you included the units, square root of 101 kilometers per hour. Because you had kilometers squared here per hour and kilometers here, so that'll cancel and you're left with your kilometers per hour. Okay, so I'm going to stop there and we'll finish up this section in the next video.